This module of the course will cover the essential aspects of the MQTT protocol that will help you to understand how to use it in your application. This lesson will focus on the MQTT control packet format for common actions that you need to perform, such as connecting, disconnecting, publishing, and subscribing. Even though most of us will never develop an MQTT library, this information is very useful to understand the key settings that are required for using an MQTT library. And understanding the packet structure will also help you to analyze the MQTT packets that are going to be captured in a Wireshark session. And we learned how to use Wireshark last week. At least we got a start on it. Unlike HTTP, MQTT is a binary-based protocol where the control packets are coded as binary bytes and not text strings. The MQTT protocol uses a command with command acknowledgement packet format. That means each command message has an associated acknowledgement message. Here we see 3 example MQTT control messages being sent from client to broker, with the associated acknowledged messages being returned from the broker back to the client. As mentioned, MQTT is a binary protocol, meaning the message control packets are constructed from coded bytes, rather than ASCII encoded strings as in HTTP. An MQTT control packet has 3 main sections. A fixed header section containing 1 byte which encodes the control packet type, followed by up to 4 bytes which encode the size of the remaining packet sections. It contains an optional variable header section which contains additional parameters that are specific to certain types of control packets. And finally, it contains an optional payload section which contains the data being sent. This format supports a minimum packet size of 2 bytes for the disconnect control message, up to a maximum packet size of 256 megabytes. Let's review some of the key MQTT client parameters that are sent in the fixed header section. The message field, which encodes the control packet type. We will cover some of these in more detail. The duplicate flag is encoded, which is used to indicate to a receiver that a message may already have been received. We'll see this used in a quality of service 1 or 2 delivery sequence. The QoS level is encoded. This indicates the delivery assurance level for this message. We'll cover QoS in more detail shortly. The retain flag is encoded. This instructs the server to retain the most recent published message and deliver it to new subscriptions. We'll also cover this in more detail shortly. Finally, we have the remaining length field, which encodes the length of the remaining packet bytes. Let's look at an example MQTT control message. After a TCP socket connection is established between a client to a server, the first packet sent from the client to the server must be a connect packet. Note that the message type is set to 1, indicating that this is a connect packet. The packet contains many session-related parameters as optional fields in the variable header section. All payload fields except the client ID are optional, and their presence is determined based on flags set in the variable header field. This slide describes each of the key fields in the variable header and payload sections, and we will cover most of these later in the course. Let's focus on the client identifier, or client ID. The client ID identifies the client and its state to the server, and must be unique across all clients connecting to the server. You choose the client ID. It is encoded as a UTF-8 string and may be between 1 to 23 characters long. Client libraries will often use a randomly generated ID if it's not given explicitly. When a client subscribes to a topic, the subscription is associated with the client ID and not the connection or username. When a message is published to a topic, the broker will iterate over all subscriptions, matching the topic, and look up if any connection is active with the associated client ID. If a connection is found, the message will be published to the currently connected device. If a device connects with a client ID that matches another connection with the same client ID, the latter will be disconnected. This is because the broker will assume that the old connection has died and that the device is just reconnecting. The CONNAC packet is the packet that's sent by the server in response to a connect packet received from a client. If the client does not receive a CONNAC packet from the server within a reasonable amount of time, the client should close the network connection. This functionality is implemented by the MQTT library connect function that you will be using. Here we see a publish control packet, which is used to transport application messages sent from a publishing client to a server or from a server to a subscribing client. Here we see a pubback control packet, which is sent by the broker in response to a publish packet with a QoS level set to 1. QoS level 0 messages do not receive a pubback, and we'll see this more shortly. The retain option is used in scenarios where clients only publish changes in data and where you want offline subscribers to receive the last known good value. In this example, we have a publisher publishing temperature data with the retain flag set to 1. This informs the broker to retain the last received publish message and deliver it to new subscriptions. When subscriber B comes back online and subscribes to the temperature topic, it immediately receives the last known temperature value from the temperature data topic. The retain equals 1 setting indicates to subscriber B that the message may have been published some time ago. Here we have the subscribe packet, which is sent from the client to the server to create one or more subscriptions. Each subscription registers a client's interest in one or more topics. Topic groups consisting of length, name, and QoS level are packed contiguously in the payload portion of the packet. The server sends publish packets to the client in order to forward application messages that were published to topics that match these subscriptions. The subscribe packet also specifies for each subscription the maximum QoS with which the server can send application messages to the client. Here we have a subscribe acknowledge or suback packet, which is sent by the server to the client to confirm receipt and processing of a subscribe packet. It contains a list of return codes that specify the maximum QoS level that was granted in each subscription that was requested by the subscribe packet. Here we have a disconnect packet, which is the final control packet sent to a server to indicate that the client will be performing a clean TCP socket disconnect, meaning it will be sending a FIN message to trigger a pair of two-way handshakes.